In this second half of Chapter 4, we're looking at the graphs of the trigonometric functions that we've been dealing with in the first half of the chapter. And as far as graphing functions, we'll be graphing the sine and cosine and none of the other trig functions. And then in the second lesson, or actually I should say lesson 4-6, I believe, we're looking at very, very limited the graphs of inverse functions of sines and cosines. All right, so a couple of basic things about sine and cosine functions. The domain for both of them are negative infinity to positive infinity. The range for both of them is between -1 and +1. Notice that the y-intercept for sine is 0, whereas the y-intercept for the cosine is 1. You also see the x-intercepts. The function is continuous. The sine function is said to be symmetrical over the origin, whereas the cosine function is symmetrical over the y-axis. So remember from way back in Chapter 1, that means that the sine function is considered an odd function, whereas the cosine function is an even function. And those of you moving on to calculus eventually, that will come into play when you start taking the derivative or the integral of these. But this is vocabulary that is 2 years away for most of you. So extrema, as I said earlier, the range of these functions is from -1 to +1, and you see that that's your maximum and minimum values for the functions. And it tells you when those extrema occur. We'll talk about that as we're kind of graphing the function. End behavior does not exist. Because this function oscillates between 1 and -1, we can't say that as the function is approaching infinity that the function values are approaching anything specific. So end behavior doesn't exist. Notice also that the cosine function looks basically like a sine function that has been shifted over. So any transformation of a sine function, or a cosine function for that matter, is referred to as a sinusoid. And our standard sine and cosine functions both have a period of 2 pi. And what that means is that every 2 pi on the x-axis, the function values repeat themselves. So we see the general forms of the equations, and the a and b values are pretty much in the exact same places where you would have expected them to be if you remember the lesson on parent functions and transformations, again, from way back in Chapter 1. Here we don't see an h value or a k value, we see c values and d values. And I believe the main reason why we're using a different value is because it represents something a little bit different. We'll talk about phase rather than a horizontal shift. And the d in this function, or in these functions of the equations, they respond, I guess you would say, the same way the k value does in way back in Chapter 1. So way back in Chapter 1, when we had an a value in front that wasn't just 1, we saw that there was a vertical stretch or a vertical compression of the function. And the same thing is happening here. We just use a different term to describe it. We say that it determines the amplitude of the function. So notice how in this visual thing I copied from the textbook, it's kind of giving a definition for an amplitude. And basically, it's half the distance between your maximum and minimum. Oh, one more thing from here. Remember also from Chapter 1 that when the a value is negative, that means that it's been reflected in the x-axis. Same thing applies here. In example 1, we're asked to describe how the graphs of f and g are related. find the amplitude of g, and sketch two periods of both functions on the same coordinate axis. All right, so I'm going to sketch f in black. And in order to kind of make this as clean and neat as I can, I'm going to make every 4 boxes on the x-axis represent pi. So 1, 2, 3, 4. Here's 1 pi. Here's 1, 2, 3, 4. 2 pi. And I may not be able to get through 2 full periods on the same coordinate axis, but since we're just getting used to these functions, I do want to make sure that I'm making it as spread out as I possibly can so that you see where all of the points are, where all of the important, I don't want to say that, but probably the points that are going to help you graph it correctly. Let's put it that way. All right, so in my basic cosine function, so I'm going to use 4 boxes to represent pi on the x-axis. I'm going to use, for the purposes of this graph, and hopefully it'll make more sense when you see the g of x graph, I'm going to represent 1 with 3 boxes. So every 3 boxes is going to represent 1. Now my standard cosine function has a y-intercept of 1. It has x-intercepts at pi over 2 and negative pi over 2, among other places. And again, I'm going to clarify that in a moment. So there's my negative pi. 1, 2, 3, 4. That's my negative 2 pi. So here is my basic cosine function. It looks like I might actually get really close to being able to squeeze 2 periods on this graph. There's my cosine function. Okay, a couple of key points that you want to realize. Again, as I mentioned, y-intercept of 1, x-intercept at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. And then again, notice these minimums of negative 1. So coming back to the question I was asked, describe how the graphs of f and g are related. G of x has amplitude of 1/3. F of x has amplitude, if I could spell, of 1. So when I graph g of x, I'm going to graph g of x in green. That means it's going to have the same x-intercepts, the same period, but it's not going to have a maximum of 1 and a minimum of negative 1. It's going to have a maximum of 1/3 and a minimum of negative 1/3. So then my maximum is here. It's still crossing through all these x-intercepts, but every time I'm hitting my mountain top or my valley low, instead of going all the way to 1, I'm only going to 1/3. So there's my 1/3. Here's another 1/3. Negative 1/3, positive 1/3, and here's its graph. Part B, the sine function. Again, I'm going to start with basic sine function in black. Remember that the sine function has y-intercept at 0, and its x-intercepts are at pi and 2 pi, and then also negative pi and negative 2 pi. I'm going to label this graph a little bit different than the last one. I'm going to label the x-axis the same way. So here is 1 pi. Here is 2 pi. Here's negative pi. Here's negative 2 pi. This time I'm going to use 1, 2, 3, 5 boxes to represent 1. Oh wait, no, I don't want to do that. Scratch that. I want to really make a big difference on the graph of f of x and g of x, but I also want to make sure that things are clear. So I'm going to use 2 boxes to represent 1. So that's 1, 2, 3, 4, 5. Okay, so as far as the difference between these two graphs, f of x has an amplitude of 1. G of x has an amplitude of 5. So start with the intercepts. As I said, the sine function, the standard sine function, has a y-intercept at 0 and x-intercepts at 0, pi, 2 pi, negative pi, and negative 2 pi. And between those is where we see our maximums and minimums. So here's our maximum of 1, here's our minimum of negative 1, minimum of negative 1, maximum of positive 1, here's another minimum, another minimum. Connect the dots. Here's our basic sine graph. Oops, I put this one in the wrong place. For the g of x function, I'm going to graph that in red. Same x-intercepts. My y-intercept is still going to be 0. Now every time I have a maximum, it's not going to be 1, it's going to be 5. Now when I have a minimum, it's not going to be negative 1, it's going to be negative 5. So this is still here, this is still here, this is still here, here, here. But everywhere there's a 1, it's becoming a 5. If there's a negative 1, it's becoming a negative 5. And when we connect the dots, last one on this screen, hopefully a little bit easier since we have the cosine function already on the screen back in problem A. And this time my y-axis I'm going to break down as there's 1, here's 2. My x-axis I'm going to label in the same manner, 1, 2, 3, 4. Here's pi, 1, 2, 3, 4. Here's 2 pi, 1, 2, 3, 4. There's my negative pi, and here's my negative 2 pi. I have a y-intercept of 1, x-intercept at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2. Which means I've got another one here and there as well. I've got a minimum of negative 1 at pi. Here. Another maximum of 1 at 2 pi. Over at negative pi, I have a minimum of negative 1 here. And at negative 2 pi here. And when I connect the dots, here's my standard cosine function. What's the difference between f and g here? F as an amplitude equal to 1. G as amplitude equal to 2. So my maximum value is 2. My minimum values are now negative 2. My x-intercepts are still in the same place. Because of what my transformed graph is eventually going to be, I'm going to make this be 2, 1, 2, 3, 4. This will be 1, 1, 2, 3, 4. Negative 1, negative 2. My x-axis, I'm going to label the same way I've been doing. 1, 2, 3, 4. Here's pi. 1, 2, 3, 4. Here's 2 pi. Negative pi, and 1, 2, 3, 4, negative 2 pi. I'm graphing my standard function in black. It will have a y-intercept of 1, x-intercepts at pi over 2, 3 pi over 2, negative pi over 2, negative 3 pi over 2, and negative 5 pi over 2, and positive 5 pi over 2. A minimum value at pi, comma negative 1. Another minimum value at negative pi of negative 1. A maximum value again at negative 2 pi and positive 2 pi. Connecting the dots, here's my standard cosine function. Now when I reflect and vertically compress this graph, my maximums of 1s will become minimums of 1/5. So I'm graphing this one in green. My x-intercepts are still going to be in the same places. But my 1s will become negative 1/5. My negative 1s will become positive 1/5. And then I connect the dots. To answer the question that was posted, how are the graphs related? So g of x is a vertical compression and reflection of f of x. I'm going to label the x-axis for part 2b in the same manner. Pi, 2 pi, negative pi, negative 2 pi. For my y-axis, I'm going to go by 2's, meaning here's 1, 2, 3, 4. My sine graph, remember, has a y-intercept at 0 and x-intercept at pi, 2 pi, negative 2 pi. Has a maximum of 1 at pi over 2, a minimum of negative 1 at 3 pi over 2, and that's kind of mirrored, not quite mirrored, but continuing in that pattern on the left side. And when I connect the dots, there's my standard sine function. G of x has an amplitude of 4, and it is reflected in the x-axis. So I'm going to do this in red. My maximums of 1 will become minimums of negative 4. My minimums of negative 1 will become maximums of positive 4. My x-intercepts are all going to be in the same places. So this minimum all the way on the left will become a maximum. This maximum here will become a, let me undo that so I don't accidentally draw through it, become a minimum. Next minimum will become a maximum, and so on and so forth. And then we connect the dots.